In this video, we continue our discussion of electrical potential. And we're going to, in this case, show how to apply the definition of electrical potential to calculate the electrical potential using the electric field. I tell you right now that while this is certainly something people test and everything, it's not the way we do it in the real world. Our whole goal is to eventually get the electric field so we can find the force, so we can then find the acceleration, so then we can integrate to find the velocity, and integrate to find the displacement. This defeats the whole purpose if we already know the electric field for wanting to then go and usually find the voltage. There are exceptions, and we'll show them, but in most cases, this is kind of the inverse of what people really do. However, if you know the electric field, it is possible easily to calculate the potential difference. I shouldn't really call this a proof. This is really just the definition that we can use that from some point A to some point B. All we really need to do is evaluate this integral and then multiply by -1. So it's an example of actually doing that. Let us take the following problem. What is the electrical potential difference between point B, which is located at this point right here, which if I go down here, best I can, is at x equal 2 and y equal 3. And I want to do this by following the following path from A to B. I want to go up to point C and then over to point B. Now, because this is a conservative force, it doesn't matter which path I take, I should get the same answer. So this is the one I'm going to do. I'm going to break this integral into two parts. And the electric field that I'm going to be calculating the electrical potential across this path for is an electric field of 100 newtons per coulomb in the x direction. Now this problem turns out not to be very difficult. It's a constant electric field and I could solve it a lot simpler, but I'm going to do it with the calculus to show you how you would do it for any problem. So the first thing to do is to break the problem up into two paths. So delta V is equal to minus the integral as we go from A to C, E dot dr, plus the integral, I should say plus, my fault, minus the integral as we go from C to B of E dot dr. Now to do this, we have to take the dot product of E dot dr, which means we need to know E and we need to know dr. Well, E is easy. That was given to us in the problem. E is equal to 100 newtons per coulomb I hat. dr in Cartesian coordinates is dx I hat plus dyj hat. It's Cartesian coordinate. And if you don't know where that comes from, it is simply having taken the derivative of the position vector in Cartesian coordinates, which is xi hat plus yj hat. I took the derivative of both sides. Now I need to do the dot product for each one of these two integrals that I have to solve. So in this case, when I do E dot dr, I get 100 newtons per coulomb times dx. So let's look at that. For A to C, well, let me do it from just A to C. Across A to C, E dot dr, we have the integral for x is equal to 0, y is equal to 0, to y is equal to 3 of 100 newtons per coulomb dx. But there is no dx. The only thing that there was dy. So this, if you prefer, another way to write this, if you had wanted to, was to leave that I hat and have dotted into dy j hat. But the j hat dot the I hat is 0. So there is no work done and no change in the voltage along the path from A to C. Now in the second integral from C to B, there is work done on the object. In the integral from C to B, E dot dr, we have in this case the integral as x goes from 0 to 2. And also we should note that y is 3 across this entire path. Now why do I keep writing that down? Because sometimes in your formulas up here there'll be a y, and if there is, you should put in the value 3 here, because that's the value of y at any point along that path. Now this is a constant. We can pull it outside. So we get 100 newtons per coulomb. And the integral dx is simply x evaluated from 0 to 2. So the integral from C to B of E dot dr is equal to 200 volts. Delta V is then equal to minus 0 volts for the first integral. This is from A to C, plus a minus 200 volts. And this is from C to B. So it's equal to minus 200 volts. And that's the answer to this problem. Like I said, this problem didn't require this much mathematics because the force due to the electric field was pointing in the horizontal direction. Thus, any displacement perpendicular to it, there is no work done by the force. The only time there's work done on by the force is when you've got a component of the displacement in the direction of the force. The same thing is true about potential. The only time you have electric potential change is when the displacement is in the direction or opposite the direction of the electric field. So if you think about this, since this was constant, this is a lot like constant forces times distance equals the amount of work done. There was 100 Newton per coulomb. We went 2 meters. 2 times 100 is 200. And of course, in this case, the units are Newton meters per coulomb. That's joules per coulomb, which we call a volt. But that's the work. We need the negative of that, so it's a minus 200. All right. Now, like I said, it is rarely that anyone actually does the electrical potential this way, because usually what we're trying to do is to find the electric field. Another